Let's say a couple of words. Let's say a couple of words. Homework. So this one, this homework is a very kind of get your hands dirty sort of homework. I want you to basically compute some Galois graphs. By the way, I think probably has anybody ever tried to compute Galois groups on like, I don't know, do you know, does anybody know if MATLAB will do it? Or Mathematica? I know that maybe, right, and I don't know what the status is of the license for Maple here. I think you still got it. I'm not sure. But anyway, so there's software where you can check yourself on this. But consider the polynomial first, x to the 5 minus 3. Let f be a field obtained by adjoining one of the complex roots of the above polynomial to Q. There is a best choice for one of the complex roots that will make doing any proofs easier. Find the degree of f over q and show that this extension is not Galois. B might look like a total non sequitur, but it is not. Show that that fourth degree polynomial is irreducible over q. There's a number of ways you can do this. You can figure out what the roots are, which is actually, if you think about that polynomial, not terribly hard to do, and argue that you can use your knowledge of the roots to make an argument that's irreducible over q, or you can use Eisenstein. Now that polynomial is not Eisenstein, but there's a way to make it Eisenstein. C, if f bar is the field obtained by adjoining all the roots of f base q, find the Galois group of f over q. And reminder, this has to be a transitive subgroup of this 5. So that will help you out. Number 2, consider the field f obtained by joining all roots of the polynomial f of x is x to the 6 minus 3x cubed plus 1 to the rational numbers. Show the complex conjugation is a non-trivial automorphism of f. Doing this one should not be too hard to accomplish. Number B, if alpha is a real root of this polynomial, show that the map induced by alpha goes to alpha inverse gives rise to an automorphism of q adjoined with alpha. And use this knowledge from A and B to find the Galois group of f over q. And 3, this polynomial, I think, looks very similar. Of course, all I've done is I've changed that the cubic coefficient to -1 from -3, but it gives something a little different. Consider this polynomial and let f be the splitting field of little f over q. A, show that there is an intermediate field E between q and the splitting field that is quadratic, such the degree of E over q is 2. And then find the Galois group of f over q and find all of the intermediate fields. For number 1, the end game can be, okay, the Galois group, I know must be isomorphic to something because I gave you a list of the transitive subgroups of S5. I did not give you a list of the transitive subgroups of S6, but you don't really need it because I think that what you do is you just kind of compute all the automorphisms and figure out what group structure is. But of course, it must be a transitive subgroup, S6 in both cases. Any questions? Okay. Right. So let us kind of pick up where we were. Okay, so the last thing that we talked about was I gave you that just truly kind of horrid algorithm for computing the Galois group of any polynomial over Q, even for quadratic polynomials so if I walk up to you on the street, I give you a quadratic polynomial over Q, the Galois group is either the identity or the Z2. And it's the identity if and only if it, if and only if it's got roots already in Q, and Z2 if not. But this algorithm, even for that situation, is pretty nasty. So, but at least you can always do that if you're completely desperate. Like if you get sent to purgatory and you can only get out one way or the other, and then this algorithm will work for you. And since you've got eternity, then maybe that's something. Okay, so I'm going to do a short little discussion on finite fields. And a lot of the stuff is going to kind of follow from stuff we've already known, but it's nice to report some of this. Proposition. If F is a finite field, so if I tell you that you've got a finite field, you tell me what can I say about it just coming right out of the gate?
It has non-zero characteristic.
Okay. It's got characteristic P where P is positive prime. And say about the order.
It's prime powered.
Characteristic that equals 0, then F contains rational numbers. So right out of the gate, if characteristic 0, then any field of characteristic 0 contains an isomorphic copy of the rationals, which is not finite, so it has to be characteristic P. How about this though? If it's, so we've established that F is characteristic P. Then what field, so we just made this observation that if you have a field of characteristic 0, it must contain rational numbers. What's the analogous statement for a field of characteristic P? It must contain some P. And here, apologies to my number theory teacher back in the day, CP, of course, refers to the integer might be and not the average. How do we get this? Well, in fact, F must be a finite dimensional extension of C, right? That's the only way for it to be finite. So let's suppose 3 is n. That means as a vector space O CP F is isomorphic to P. Whatever. So So if, so I know that for every prime, there is a finite field of order P, right? Namely, C. P. I also know that if characteristic of the field, if the field is finite, it's characteristic P, then, well, then any finite field that I might find of characteristic P has P to the n elements. What is the obvious question, I think, after that? Or what is an obvious question, I would say? I think one question is, so here's what I know. This proposition tells me that if I have some finite field, characteristic P, then it has that P in elements. The other side of that question is, okay, suppose I give you a P to the n. Is there a field of that size? I know this is true for n equals 1 for every P, but is it true that there's a field of order P squared for every P? Is there P cubed and so forth and so on? So the answer is going to be yes. We'll build to that. First, theorem. I'm not going to prove this because you already know this in a certain sense. You've done it in the homework, but it's good to record it here. Let F be any field and E a finite subgroup of F star multiplication. So that's the F star, I mean, the group under multiplication of non-zero elements in the field. Then B segment. So in particular, yeah, if only finite. So we'll say that the order of F is P to the n. Then F star is sigma of order P to the n. Okay. I will leave that proof here. Oh, well, I mean, your homework on this has already been due, zero C proof. Right, but I think everybody kind of nailed this one. Okay, let me give you a corollary, which is interesting. Let F be a finite field characteristic P. So we have to see finite field and characteristic P. Then. That's kind of a good thing to know, right? So if you have a finite field, it's always ZP adjoined with a single element. F and CP adjoined with U, where anybody want to guess what U is or what a good choice for U would be? That's why it's a corollary. Just take, you know that F star has a cyclic generator, right? Call it U. Just stick that on the ZP. In fact, not only will U by itself generate everything that you need, it actually also generates the ZP for free. In fact, the only thing you need from CPU is the zero element, right? Because multiplicative, as U runs through its powers, it picks up everything in F star, including all the stuff in ZP, with the exception of zero. Right? So zero is all you need. In addition to that, U. Okay, so now we're going to introduce something called right, Prometheus. So what about 864? Let F be a field of characteristic P and R an integer. Then map given by so the map given by take x to the p to the r power is a ZP monomorphism of fields. F is finite. And PR is one of those. Okay. The map uh, Actually, I don't know. You know, my fault. I'll disclose name. Let's get proof of this. Well, the important thing is characteristic P. Note that P from F to F is given by, in my notation there, P1 is given by P of X equals X P. Then P is a homomorphism. Indeed, since everybody proved this like in the beginning out of the class or first edition, whatever. The freshman's range, this is of course because you've got characteristic B and B so P of X plus Y is P of X plus P of Y, P of X Y is P of X P of Y. So homomorphism. Right? Can somebody explain? I did say it's CP monomorphism. Right? Well, also note that we have X to be ZP, then I know familiar with this fact. Right? I can actually notice that ZP star is cyclic for P minus one. Right? So if it's not zero, then X to the P minus one equals one. You all are quite familiar with this in terms of, especially if you're a big fan of photography. This is from Miles' Little theorem that which is stated in terms of the integers. If A and P are relatively prime, then A to the P minus one is equivalent to one by P. Multiply both sides of this equation by X, and I get X P equals X, which I've always thought was a superior way of thinking about this, because this incorporates all elements, including zero. So what do we got here? We have, in the case of R equals one, that this is a ZP monomorphism of fields. And we also know if F is finite, then, well, let me start with that phrase. Let me start with this one. Now, P is 1, 1. Right? Because what have we just said? We've shown that this is a homomorphism of fields. Right? And we've shown earlier in class that if you have any homomorphism between fields, then it has to be 1 to 1. unless you're one of those crazy people that wants to count zero math, which this is clearly not, because phi of one equals one, right? So note that phi is 1 to 1. So if f is finite, then phi is onto. So I think we have a complete proof of this in the case that, R is 1. How do we go from here? By induction. I think there's note. P R plus 1 is equal to so you see all the statements go away. Okay. Any questions? Let me give you a theorem here. And then I wanna, after this theorem, I want to do a follow up this. Any questions? Uh, Theorem 865. This is really kind of proving. Suppose P is a positive prime and N is an integer. N is an natural number, say. Then F is a finite field of order P in the N. If and only F is the splitting. Uh, uh, Now, let me make a comment here. You can do the splitting field for any polynomial you like, right? For example, I could take the splitting field of x squared minus 1 over the rationals. It's a bit of silliness, right? Because plus and minus 1 are already rationals, but the splitting field would be the rational already split. I point this out because we're used to dealing with theory. I mean, this thing's got a lot of roots to it that are already in CP. In fact, everything in CP is already a root of this. Notice zeros root of this, no one is, and so forth and so on. So I'm not claiming that's irreducible, but let me sketch it anything. Suppose The cyclic order, in particular, then so if you have an arbitrary element, call it X, although I guess I'm using the notation over here. Notice that X to the P to the N minus one is equal to one. Correct? Multiply this by X. And since X is in F star, assume it's not zero. So this holds for all X non-zero X in F B F X and zero. Right, the equation I got was constructed and it worked for every non-zero X. What a bonus, zero too. So all X in F is a root. I really should have used another notation. Sorry. So everything in this field of P to the N elements is a root of this. Now, here's the potential problem. How do I know it's the splitting of this, right? Because what do I know? I know that every element of this field of P to the N elements is a root of that polynomial. Right? So, how do I know that the splitting field is smaller? Okay. For example, if you go back to my example earlier, x squared minus one, the splitting field of that is the rational numbers, right? But, you know, you didn't really need that polynomial. There might be extraneous things. I claim that this polynomial is 7. Does anybody see why that's true? Can you provide? What's the derivative of this number? -1. Wasn't that the characteristic B, but and well, in particular, this is not zero. So f of x is 7. Well, now let me be a little bit more careful. This is not irreducible, but what we do have is GCD of f prime is 1. So f has no multiple roots. Even though this polynomial is not reducible over ZP, we know it doesn't have multiple roots, so it's 7. as claimed. In particular, has exactly P and N distinct roots. So it's gotta be the splitting field, right? Because remember, splitting field, if you take the ZP, in this case, Z mod P, and you join all the roots, what, it takes them all, doesn't it? Yeah. So let's do a couple. Oh, the other direction, I didn't say, so the other direction, if F is the splitting field of this, right? We need to show that F is a finite field. Well, all you have to do is in the other direction. Exactly the same way we did before. That means this thing has P to the N distinct roots. And it's easy to show that those roots form a subfield or form a field. Right? And that basically follows from our arguments about freshman stream and the convenience. Any questions on that though, before I stampede off? So here's, let's look at an example or two. Let's look at fields of order 9, right? This should be the splitting field. Of it should also be quadratic extension. See what vector. Because it's 9 elements, it should be as a vector space, 2 copies of C3. So it should be a quadratic extension of C3. It's a splitting field of this 9th degree polynomial. Let's try to factor and see if we can get any insights. How did they two poly? So how can we factor this? Well, this is X. Well, so I'm factoring this over Z3. This is. Right. Now, this one's gonna. Okay, right, nice. Now, x squared, x squared plus one is irreducible over z three. Right, right. I gotta do this test for roots. X4 plus one is a bit of a mystery to me, though, right? Because is it clear to you all that x4 plus one doesn't have any roots over z3? Right? I mean, you plug in one, you plug in minus one, you plug in zero, none of the roots. Well, what could happen here? This could break down into irreducible quadratics. In fact, I bet it does. This is quadratic polynomials over Z3. Yeah, unfortunately, with 9 x squared plus 1, x squared minus 1, x squared plus x, x squared plus x plus 1, x squared plus x minus 1, x squared minus x squared minus x minus 1, x squared minus x plus 1. I want to circle the ones that are irreducible. Can you all identify them? Certainly not, certainly not, certainly not, certainly not. None of those are irreducible. This one is, because it's not got no roots. This one has a root, namely 1, so it's not irreducible. Remember, we're mod 3. This one has a root, namely -1. I agree with that. I'm left with 2. I will bet you that these two are not only irreducible, but their product is x to the 4 plus 1. Let's see what happens when you multiply this. That's x4. Then I'm going to have minus x cubed plus x cubed. So that's gone. I'm going to have minus x squared, minus x squared, minus x squared, minus 3x squared, gone. I'm going to have x minus x, gone. I'll have, so my final factorization is here. 0, 1, minus 1. Right? Those are the elements of Z3. Right? This leaves me out of a field of 9, 6 more elements. Right? Two of them roots of this, two of them roots of this, two of them roots of this. So I did notice that this is a quadratic extension. So you could also just take ZX and join the root of this, square root of -1. Or you can join the root of this or root of this. And all three of those will give you isomorphic fields. So once you join the square root, you automatically get the other two solutions of this. Okay, any questions on that? Let's do one more. So basically, you see everything kind of shed out for you. This should be a cubic extension. C2. Now, if I factor x to the 8 minus x, this is x times x to the 7 minus 1. Well, I can pull an x minus 1 out of that, giving me x to the 6 plus x5 plus x4 plus x3 plus x2 plus x plus 1. So since we're running low on time today, let me ask for a bold prediction from you. Can I factor this any further over C mod 2? What do you predict I'm going to get?
I'm gonna predict that it factors in the 2 cubics.
That is exactly right, because this extension has to be cubic. I bet you will find that there are exactly, if you look at all the possible cubics over Z2, and there should be 8 of them, right? Throw out the ones that are reducible because you've already got them covered. You will find that there are exactly 2 irreducible cubics. And if you multiply them, that's what you get, right? And so hopefully this gives you some insight, because the splitting field, it gives you the roots of the base field. And if you want to do something really exotic, why don't you do, oh, this would be great, do the field of 64 elements, because that's a degree 6 extension of Z2. It's a 64-degree polynomial sense of pain, but you can probably work it out on like MATLAB or some get a factor. And what you should see is linears that correspond to the base field, and then you should get the irreducibles for the intermediate extensions, right? The irreducibles of degree 2, 3, and 6. So, okay, any questions on that? All right, well, my former student Brandon is here, and he's going to give a very interesting talk today. I encourage y'all to be there at the Math Club. Other than that, I will see you all on Monday.